All right. So we'll go ahead and get started. So just make sure everybody can see that, right? Everybody's all right, cool. So this, I went over this a little bit at the end of the module 1 study session, but we'll kind of just touch it again, the net change and the average rate of change of a function. So the average rate of change of the function y equals f of x between x equals a and x equals b it's basically just the change in y over the change in x. So there is a secant line between the change, basically where your a value and your b value is, that's called the secant line. So this is the slope. Basically, the secant line is just the slope of the average rate of change. So the net change is going to be your change in y. So whenever you find average rate of change and net change, if you find net change first, then you don't really have to do it again. You can just take your net change and put it over your change in x. So it's kind of like saving you some work here. But average rate of change is going to be your change in y over change in x, or the net change over the change in x. So you're taking your y2 minus your y1 over your x2 minus your x1. So there's an example here. Function is given, determine the net change in the average rate of change from f of z equals 1 minus 3z squared. And you're given that z equals -2 and z equals 0. So you just plug in those numbers there to get your net change first. So it's going to be f of 0 minus f of -2. So you're going to plug in f of 0 into this equation here and f of 2 into this equation here. So you get 1 minus 3 times 0 squared minus 1 minus 3 times -2 squared. So just multiplying it all out, subtracting it all out, you get 1 minus 0 minus 1 minus 12, which is 1 minus -11, which is 12. So that's your net change. So yes, the x2 will always be the value that is greater. So 0 is greater than -2. So that's going to be your 2 right here. This will be your x sub 2 that you're subtracting, or your y sub 2 in this case, because it's net change. So basically just whichever one is greater is the one that you're going to take first, like subtract it. Exactly. That's exactly what it is. Average rate of change is going to be that secant line right there. So it's a slope, same thing as slope. Yep. All right, so then you take your net change over your change in x. So your change in x will be, here's your x's right here, -2 and 0. So you're taking that 12, which was the net change that we found, and you're taking 0 minus -2. So it's 12 over 2, which is 6. So this is the graph of the function that we just looked at, 1 minus 3z squared. And you can see that the slope of the secant line, the average rate of change, is 6, because we're going over 2 and up 12. So 12 over 2. And you can see that the net change here is, what did we say the net change was? 12. So you can see it's 12 in the net change. That's your change in y from these 2 points, from x equals 0 to x equals -2. Okay, moving on to transformations of functions. This is 2.6 of the textbook. So vertical shifts of graphs. Basically, you're either adding or subtracting to the f of x right here. So adding or subtracting will shift the graph upwards. Adding will shift the graph upwards, and subtracting will shift the graph downwards. So this is a vertical shift that's adding, and this is a vertical shift that's subtracting. Horizontal affects the x values. So this is going to be, if inside of the f of x you have x minus c, then you're shifting to the right. Remember, it's opposite. So if it's a negative sign, you're shifting to the right. And if it's a positive sign, then you're shifting to the left. So vertical shifts are up when adding, down when subtracting. Horizontal shifts are to the left when adding and to the right when subtracting. And vertical affects the y values and horizontal affects the x values. And what I mean by that is that you can see if you have a vertical shift and say it's +1, it's going to affect all your y values. So that if this was your f of x right here and you're adding 1 to it, it's affecting all of these y values. It's adding 1 to them. So you're shifting up by 1 for everything. So same thing here. The horizontal shifts affects the x values. So when you have a minus or subtract here inside the parentheses with the x, then you're changing the x values. So you're either adding, say it was 2, say you're subtracting 2, so then you're going to be moving to the right 2. All right, reflecting graphs. To graph y equals negative f of x, reflect the graph in the x-axis, and to graph f of negative x, reflect the graph in the y-axis. So when the negative affects the y values or f of x, it's reflected on the x-axis because the y values are changing to negative. So you can see here, if this was f of x and then you take the negative sign before f of x is also known as y. So you're basically saying negative y here. So when you change these positive y values to a negative, then it's flipping it over the x-axis. So same thing here, when the negative affects the x inside of f of x, you're affecting all the x values. So that's why it's reflected on the y-axis. It's because say you had over here, you had the x value was 1, and you're changing it to a negative 1. So then you would have over here your f of negative x. Vertical stretching and shrinking of graphs. So if the number is greater than 1, then you're stretching the graph vertically by a factor of c. And if it's a fraction, then you're shrinking the graph. And horizontal is going to be opposite. So that's one thing to remember, is that horizontal is opposite than vertical stretching or shrinking. So when doing vertical stretching or shrinking, multiply the y values by c. Fraction means shrinking, number larger than 1 means stretching. So if you see right here where the C is, if you see a 2 right there, then you're stretching vertically by a factor of 2. If you see a 1/2 there, then you're shrinking vertically by a factor of 1/2. So you're multiplying your y values, your f of x, by whatever that is. Horizontal shrinking and stretching of graphs. So it's the opposite. So if it's greater than 1, then it's going to be a shrink. And if it's a fraction, then it's going to be a stretch. So when doing horizontal stretching or shrinking, divide the x values by c. Fraction means stretching, number larger than 1 means shrinking. Like I said, they're opposite. So say that you had, let's see, shrinking the graph. So it's divided it was f of 2x. Then you are going to divide the x values by 2. It says my internet connection is unstable. Can you guys still hear me?
Yeah, you broke up for a minute.
Okay.
You're good now.
All right. So the notes have this a little bit differently than what I've read is the actual order of transformation that you want to follow. So as long as you're following basically PEMDAS when you're doing these, then you're doing it in the right order. I think sometimes you can get the wrong answer by doing it out of order, but the main thing is to always start with what's in the parentheses, because remember, parentheses comes first in PEMDAS. So you look for a possible horizontal shift. So then you can deal with the multiplication, which is a stretch or compression. Then you deal with negation, which is a reflection. Then you deal with addition and subtraction, which is a vertical shift. So it's basically following the order of operations. It's like this, like anything inside of these parentheses, you're going to work on first, which is going to be a horizontal shift. Anything inside of these, this is what's going to be next, is a vertical shift, or excuse me, you're going to deal with horizontal shifting first, then horizontal stretching or shrinking. Then you're going to deal with the multiplication for vertical stretching or shrinking. Then you're going to deal with vertical shifting. So that's the order. That's just following PEMDAS based on this equation right here. So just some examples. F of x minus 5 plus 2 means that we're going to shift to the right 5 units because we're affecting the x values, and then shifting upwards 2 units. F of x plus 1 minus 1 is shifting to the left 1 unit and downwards 1 unit. Negative f of x plus 5 is reflecting about the x-axis, because you think about it, we're affecting the y values, so we're going to reflect on the x-axis. Plus 5, so we're shifting upwards 5 units. 2f of x plus 5 minus 1 means shift to the left 5 units. We're doing that one first. Stretch vertically by a factor of 2, and then shift downwards 1 unit. So 1/4 f of x minus 3 plus 5 means shifting to the right 3 units, shrinking vertically by a factor of 1/4, and shifting upwards 5 units. Y equals f of 4x just means shrink horizontally by a factor of 1/4. So you can basically, you're just dividing x by 4. So that means that you're shrinking by a factor of 1/4. It's the same thing as multiplying by 1/4 or dividing by 4. y equals f of 1/4 over x, you're stretching horizontally by a factor of 4, because remember, when it's less than 1, it's going to be a stretch for horizontal stretch shrinking. It's the same thing as dividing by 1/4. So y equals 2f of 1/2 x minus 4 plus 7. You're shifting to the right 4 units because we're affecting the x values in here. Stretching horizontally by a factor of 2. It's like dividing by x by 1/2. So that means we're stretching by a factor of 2. Stretching vertically by a factor of 2 and shifting upwards 7 units. So just kind of showing how all the transformations are working there. And this is just basically the equation in which the transformations are expressed. So here's the graph of that last one that we looked at. You can basically see that the graph of x squared here, this is just a transformation to the graph of x squared. So it looks like this, and then we are changing it, we're shifting it to the right 4 units, shifting it up 7 units, and stretching it vertically and horizontally by a factor of 2. Even and odd functions, let f be a function. F is even if f of negative x equals f of x for all x in the domain of f, and f is odd if f of negative x equals negative f of x. So this just kind of shows how they look. An even function is symmetric with respect to the y-axis. You can see the y-axis right here, and it's the same on both sides. And then the graph of an odd function is symmetric with respect to the origin. So to determine whether a function f is even or odd or neither, you just replace all the x's with negative x. So right here, so we can determine both even and odd by just seeing f of negative x and seeing what f of negative x equals. So if we're given f of x equals x to the 4th, then we're going to see what f of negative x equals. So f of negative x for x to the 4th, you just replace all the x's with, so you replace this x to the 4th with a negative x. So anything that's a negative raised to an even power is going to be positive. So you can see that negative x to the 4th equals x to the 4th. So that means, therefore, f of negative x equals f of x. So that means it's even, just like we saw up here. F of negative x equals f of x. If it's the same thing, then it's even. And if f of negative x equals negative f of x, then it's odd. So then we're given f of x equals x to the 3rd minus x. So we're just going to replace all of the x's with negative x. So we take f of negative x and we get negative x to the 3rd minus a negative x. And that equals anything that's negative raised to an odd power is still going to be negative. So we get negative x to the 3rd plus x, because minus the negative x is plus x. So then we can see by distributing out this negative sign, we get negative x to the 3rd minus x. See, all we did was just take the negative out of here to see if f of x equals, or f of negative x equals negative f of x, and it does. So this is an odd function. So then we've got 2x minus x squared. We take f of negative x, so we get 2 times negative x minus negative x squared, which is the same thing as negative 2x minus x squared, which equals negative, we're factoring out that negative sign again. We get negative 2x plus x squared. So that this negative, we're trying to get to 2x minus x squared. And since we factored out this negative sign, it doesn't equal either one of them. F of negative x doesn't equal negative f of x, and f of negative x doesn't equal f of x, so it's neither. All right, combining functions. So when you're given f plus g or f minus g or fg and f divided by g, they're defined as follows. So all three of these, the f minus g and the fg, they all have the same domain. It's just going to be the domain of f of x intersected with the domain of x. So find one, say you started f plus g, you don't have to find the rest of these. Your domain is going to be the same thing according to this property right here. The only one that is sometimes different is going to be f over g of x, because g of x cannot equal 0. So it's still going to be a intersect b. It's still going to be the domain of f of x combined with the domain of g of x, but with the restriction that g of x cannot equal 0, because g of x is in the denominator right here. So we'll just do some examples. Find f plus g, f minus g, fg, and f divided by g in their domains. If f of x equals 5 minus x and g of x equals x squared minus 3x, then find f plus g of x, which is the same thing as taking f of x plus g of x. So you just set it up just like that. 5 minus x plus x x squared minus 3x, which gives you x squared minus 4x plus 5, because we've got the x squared that we're adding here, minus 4x, we got a negative x plus a negative 3x, and then we've got the 5 here. So the domain of f of x is, you're looking at f of x, 5 minus x. So the domain of f of x is negative infinity to infinity. And the domain of g of x is negative infinity to infinity, because it can equal anything. There's no restrictions on this, on either one of these two domains. So the intersection of the domains is just negative infinity to infinity, because they're the same. So once you found f plus g of x, you already know that f minus g and fg are both going to be negative infinity to infinity. And you can check it if you want to, but you don't have to do that work over again, because you already know, according to this property up here, they're all going to be the same. The only one that's different is going to be f over g of x. Sometimes it's still the same. So f minus g of x, you just do the same thing. You take 5 minus x squared minus 3x, which gives you a negative x squared plus 2x plus 5, because negative x minus a negative 3x is positive 2x, and 5 minus nothing is 5. So still got the same domain as f plus g. So then you got to find f times x. So f of x times g of x. So you just multiply them together, expand it out. You've got the 5 minus x times the x squared minus 3x, which gives you 5x squared minus 15x minus x to the third plus 3x squared. And then simplifying it out, we've got negative x to the third plus 8x squared minus 15x. Still got the same domain as the other two. So this one, we know that g of x cannot equal 0. So we're setting it up just like f of x over g of x. We've got 5 minus x over x squared minus 3x. So we know that x squared minus 3x cannot equal 0 because it's in the denominator. Remember, g of x cannot equal 0. So we know that x can equal 3 and x can equal 0, because when x equals 0, the denominator is 0. And when x equals 3, you've got 3 squared, which is 9, minus 3 times 3, which is 9. 9 minus 9 is 0. So the domain is going to be an intersection of negative infinity to infinity with the restriction that g of x cannot equal 0. So that means that we're going to go negative infinity, and it cannot equal 0, and it cannot equal 3. So it's just an intersection of the domains that we had before with the restriction that g of x cannot equal 0. So that's the domain. So we'll do one more. F of x equals 2 over x, g of x equals 4 over x plus 4. So f plus g of x, we're adding fractions here, so we have to find a common denominator to be able to add them. So the easiest way is to just take this denominator here, this x plus 4, and multiply it by the 2 over x so that we can get a common denominator. And then you're going to take the 2 over x and multiply it by, I already said that. You take the 4 over x plus 4 and multiply it by x over x. So you get a common denominator of x times x plus 4. So you've got 2 over x times x plus 4 over x plus 4 gives you 2x plus 8 over x squared plus 4x. So same thing here. You're just trying to find a common denominator. So we take 4 over x plus 4, multiply it by x over x, and that gives us 4x over x squared plus 4x. So now we can add these together. So we just take this, what we found here, and what we found here for g of x, and now we're just going to add them together. So 2x plus 8 over x squared plus 4x plus 4x over x squared plus 4x. That gives us 6x plus 8 over x squared plus 4x. So you got to do the domains separately on these ones. So the domain of f of x is x cannot equal 0 because it's 2 over x. So x cannot equal 0 for f of x. And the domain of g of x is x cannot equal negative 4, because if we have it as negative 4, then the denominator equals 0. So x cannot equal negative 4 and x cannot equal 0. That's the intersection of the domains. That's what they mean by A intersect B. So intersection of the domains f of x and g of x. So then you get negative infinity to negative 4 union negative 4 comma 0 union 0 comma infinity. All right, so then we've got, we already know that we found a common denominator before, so now we can just subtract these. So you're doing f minus g of x. So you just take the 2x plus 8 over all of this stuff minus the 4x over all of this stuff. And that gives you negative 2x plus 8 over x squared plus 4x. So again, f minus g and f times g are going to have the same domain as f plus g. So we already know it's the same one. So then we have f times g of x. So now we're just going to multiply f of x times g of x. So we can just do this by multiplying across, because when we're multiplying fractions, you multiply the numerators together and you multiply the denominators together. So you get 2 times 4 is 8, x times x plus 4. Then you've got 8 over x squared plus 4x. The domain is still the same thing because we've still got this in the denominator here. All right. So then this is an example where the domain is actually the same for f over g of x. So you've got 2 over x over 4 over x plus 4. So with dividing fractions, it's a times d over b times c. So it's going to be the 2 times x plus 4 over 4 times x. So that gives us 2x plus 8 over 4x. It really helps just knowing you're multiplying and the rules with fractions. So that simplifies to, if we divide everything by 4, that simplifies to x plus 4 over 2x. But remember that it's the intersections of the domains of f of x and g of x for this entire thing. So you can't have g of x equals 0 or be undefined. And g of x is right down here. So the domain is still the same thing, negative infinity, -4, union -4, comma 0, 0, comma infinity. So again, with intersecting domains, it always talks about A intersect B. So you find the domain of f of x, call this A. Find the domain of g of x, call this B. For example, say that the domain of f of x is x equals 2. X cannot equal 2. So that means that the domain would be negative infinity, comma 2, union 2, comma infinity. So say that the domain of g of x is x. The domain of g of x is greater than or equal to 0. So we've got a bracket here and 0, comma infinity. So you combine those two domains to find A intersect B. So we're just combining this domain here with this domain here. And that gives us 0, comma 2, union 2, comma infinity, just combining the two domains. So just remember that for f over g of x cannot equal 0. Sometimes you're asked to evaluate all the combined functions that you found. I don't think that it'll be like this on this test, but in homework and everything like that, sometimes you're asked to evaluate each combined function at a given value. So like for x equals 4. So you just plug in 4 for everything, and that's pretty straightforward. It's just plugging in anything for the x's. So we don't really have to go over that. I just thought I would include it. So let's go on to graphical addition. So graphical addition means basically just adding two graphs together. So when you have f plus g of x, you're adding f of x to g of x. So say this is f of x and this is g of x, and we want to add them together to see what the new graph would be. So you're just adding the y values of this one to the y values of this one to obtain the graph of f plus g of x. So say that we had this was equal to 1 and this was equal to 2. Right here, if f of 2 was right here and g of 2 is right here, and we added them together, then that would give us this value right here. So you're just adding the y values together. Composition of functions. So suppose that f of x equals the square root of x and g of x equals x squared plus 1. You want to find f composed with g of x or f of g of x. So anytime you see a function that is composed this way, with this little composition symbol, it's just basically you want to take the last one and do that one first. So that's just saying f of g of x. So the first thing you want to do is find g of x and then take the f of that. So g of x equals x squared plus 1. You're going to substitute g of x into f of x as the x. So f of x is a square root of x. So then you're just going to take the square root of g of x. That's all you're doing. So it's going to be the square root of x squared plus 1. There's this neat little function machine diagram here that shows what happens when we do g of x. So if you put x into the function g, then you're going to get x squared plus 1. And if you put x squared into the function f, then which is the square root of x, then you're going to get the square root of x squared plus 1. It's just, I don't know if those machine diagrams help anybody, but it's kind of helps sometimes to see it in a picture. So then you don't want to do the reverse. You want to do g of f of x. So you substitute f of x into g of x as the x. So since g of x equals x squared plus 1, then we're going to take everywhere that we see the x, we're going to put the square root of x because that's what f of x is. So we're substituting in here, since it's x squared plus 1, it's going to be the square root of x squared plus 1, which is x plus 1. And then sometimes it'll say f of g of 5, which is just saying f of g of 5. So you want to find g of 5 first, because that's what it's asking you for. It's asking you to find f of g of 5. So you're going to find g of 5 first. So you're just plugging it into 5 squared plus 1. It's just 25 plus 1, which is 26. So then you're going to substitute the g of 5 that you just found, or 26, into x for f of x. So since it's the square root of x, then you're going to just do the square root of 26. And then g of f of 5, same thing. Find f of 5 first. So the f of 5, since it's the square root of x, is going to be the square root of 5. Substitute square root of 5 over f of 5 into x for g of x. So since it's x squared plus 1, you're going to take that f of 5 that you found, which was the square root of 5, and you're going to square it plus 1, which is 5 plus 1 equals 6. Composition of three functions. So it's still the same principle here. So when you have f of g of h of x, so you basically want to find g of h of x first, because that's what it's asking you to. It's asking you to do h of x, which you're given, and then you're going to do g of h of x, and then you're going to do f of g of h of x. So say f of x equals x to the fourth plus 1, g of x equals x minus 5, and h of x equals the square root of x. So you're finding g of h of x first. So you're just replacing the x and g of x with h of x. So since g of x is x minus 5, and we just take this h of x and put that in there for the g of x, that's how we find g of h of x. So it's going to be the square root of x minus 5. So then you're going to take this whole answer that you found g of h of x, and you're going to plug it into f of x. So anywhere that we see the x for f of x, we're going to just put this whole thing right in there. So it's going to be the square root of x minus 5 to the fourth plus 1. Okay, expressing a function as a composition. This is kind of like going in reverse order and breaking it down. So express the function in the form f of g. So this basically means just find the functions f and g such that the function equals f of g of x. So when you're looking at something like this, I like to notice what it has in common. What's something that could be an x and be replaced in there a couple of times? You know what I mean? So it's like, notice that x squared is in the function twice. So that could be like a placeholder, since that's in there twice. So say that g of x equals x squared, then replace all the x squared with x to find f of x. So if you can kind of play around with it a little bit. You just say that f of x was x over x plus 4. You can go back and check your work to see if f of g of x gives you the same g of x. So if g of x was x squared, and we plugged it in to this f of x, then we would get x squared over x squared plus 4, which is the same thing as g of x. It's a little bit different when you have one that's f of g of h, which means find functions f, g, and h such that the function equals f of g of h of x. So we're getting that g of x, big G of x, equals 4 plus the cube root of x all to the 9th power. So with these ones, with the larger ones, I like to start with the outermost operation of the function. So everything inside the parentheses is raised to the 9th power. So that's how I know it's going to be my f of x. That's the outermost thing that's happening with the function. So say that f of x was x to the 9th. So this is going to be, that leaves you with 4 plus the cube root of x. So say that that's going to be your g of h of x right here, because now you can just see, let's see, 4 plus x. If you made h of x the cube root of x, then you would have g of x as 4 plus x. Sorry, it's kind of hard to explain this, so I'm just going to do the best that I can. But checking your work starting with g of h of x, you can just try to see if these things that you've worked out, see if they work. So if you take g of h of x, say h of x is the cube root of x, and you plug that into g of x, you get 4 plus the cube root of x. And then if you plug that into f of x, all of that into f of x, you just take it all to the 9th power. If we said f of x was x to the 9th, then we come up with f of g of h of x equals 4 plus cube root of x to the 9th, which is the same thing as g of x. So just basically starting with the outermost part of the function definitely helps with that. All right, one-to-one functions and their inverses. So basically a one-to-one function is when no two elements have the same image. So you're not going to get the same y for any input that you have. For any of these x's, they're not going to equal the same y. You're not going to have 4 going to 10 and 4 going to 7. They only go to one corresponding y value. That's what it means by 1 to 1. So you can see that both 3 and 2 go to 4 over here, so it's not 1 to 1. You can also tell if a function is 1 to 1 if it does not pass the horizontal line test, then it's not a 1 to 1 function, because you can see here there's two corresponding y. These two different x values have the same corresponding y values. So that's saying the same thing. It doesn't pass the horizontal line test, so it's not a 1 to 1 function. It has to pass the horizontal line test. So you can see the cube root function is a 1 to 1 because it passes the horizontal line test. There's no y value that corresponds to any of these x values, the same thing. So determining whether a function is 1 to 1, you basically just want to see if any of the x's have the same y value. So if you have x squared minus 2x, then you see that if you have f of 2, that equals 0, because if you take 2 squared minus 2 times 2, which is 4 minus 4, that equals 0. And also f of 0 is 0 squared minus 2 times 0 equals 0 minus 0, which equals 0. So two different of these elements, two different x's, have the same image, which is 0. So therefore, it's not 1 to 1, because you can't have two x values have the same y value. So sometimes it'll give you a domain for the function. It'll be a restricted domain. So if you got r of t equals t of t to the 6th minus 3, for the values t is greater than or equal to 0 and less than or equal to 5. So this is over a certain domain. So it's kind of a little bit of work, but I like to just check to see if there's anything the same over any of those values, and you can just kind of see the trend. So I just took t of 0, which is -3, t of 1, which is -2, and just work them all out and see over this entire domain if any of these values have the same output. And if no elements have the same image, then the function is 1 to 1. Image is just like the y value. So the inverse of a function. So a function has to be 1 to 1 for it to have an inverse. So basically, you just have, if you're given an f of x, to get back to that x, you have to take the inverse. So it shows it a little bit better down here. So it says find f of 1 equals 5. If f of 1 equals 5, f of 3 equals 7, and f of 8 equals -10, find f to the -1 of 5, f to the -1 of 7, and f to the -1 of -10. So f to the -1 is just the inverse. So basically, you're saying this is the function f right here. So you're taking f of 1, which gives you 5. So to get back to 1, you take the inverse function. So you're taking f to the -1 of 5 equals 1. So since f of 3 equals 7, f to the -1 of 7 equals 3. And since f of 8 equals -10, then f to the -1 of -10 equals 8. You're just going backwards. Finding the values, inverse values from a graph of f. So it's the same thing. So you can look at f of 4 here. F of 4 is right here. So then you can also say that f to the -1 of 3 is 4, because you're saying f of 4 is 3. So same thing. If you're saying f of 7 is 5, then f to the -1 of 5 is 7. So that's how you look at it from a graph perspective. All right, the inverse function property. So when you have two 1-to-1 functions and you want to determine if they're inverses of each other, you have to basically compose them together and see if they both equal x. So the functions, if f and g are 1-to-1 functions and f of g of x equals x and g of f of x equals x, then we say that they're inverses of each other. So the domain and range for an inverse function will be switched. So if you're given a function f of x equals x cubed, which is just the cube function, then for the inverse function, which is the cube root of x, you can just see that this is the domain here, and the domain and range are switched. So we took all these x values and made them the y values, and all these y values, we made them the x values over here. So you can also see that inverse functions are reflections of each other in respect to the line y equals x. So this red line right here is x cubed, and this is the cube root of x. So then if we have the line y equals x right here going through, then we can see that it's just a reflection over the line y equals x. All right, so using the inverse function property to show that f and g are inverses of each other. So we're basically just going to take this f of x, we have 1 over x minus 1, and g of x equals 1 over x plus 1. We're going to do f of g of x by composing functions. So we've got, we're just replacing this x right here in f of x with the g of x. So we've got 1 over x plus 1 minus 1, which is the same thing as 1 over x, which equals x. So then we're taking g of f of x. So we're just replacing that x right here with everything right here. So we're going to have 1 over x minus 1 plus 1, which is the same thing as x minus 1 plus 1, which is the same thing as x. So both equal x, therefore they are inverses. Same thing as another example, f of x equals 3x plus 4, and g of x equals x minus 4 over 3. So we're composing these functions here. F of g of x, we're just taking this x right here and replacing it with g of x. So we've got 3 times x minus 4 over 3. And if we multiply by 3, something that has a 3 in the denominator, then it's just going to be x minus 4 plus 4 here. So we've got x minus 4 plus 4 equals x. G of f of x. So we're taking this x and g of x and replacing it with f of x. So we've got 3x plus 4 minus 4, which is the same thing as 3x over 3, which equals x. So they are inverses of each other because both f of g and g of f both equal x. How to find the inverse of a one-to-one function. So the first thing you want to do is write y equals f of x. So instead of having it be f of x equals 2x plus 5 over x minus 7, you're going to have it be y equals 2x plus 5 over x minus 7. Then the next thing you're do is going to solve for the equation in terms of x. And then you're going to interchange x and y. You can also interchange x and y at the beginning if you want to. It's really just up to you. I like to do it at the end, but it's really up to you. You're going to get the same answer as long as you remember to interchange x and y. So finding the inverse function, the first thing we're going to do is write it as y equals f of x. So we've done that. Then we're going to solve for x. So we're going to multiply both sides by x minus 7. That gives us y times x minus 7 equals 2x plus 5. So then we're going to distribute the y right here. So we've got xy minus 7y equals 2x plus 5. Sometimes you got to play around with these a little bit to figure out how you can solve for x. It's just going to take some algebra to get there. So then what we're going to do is we're going to add a 7y to this side, and we're going to subtract a 2x on this side so that we can get the x's all on one side. So we've got xy minus 2x equals 7y plus 5. So then we're going to factor out the x here. So we've got x times y minus 2 equals 7y plus 5. So then if we divide both sides by a y minus 2, then we solve for x. We've got x equals 7y plus 5 over y minus 2. So we interchange our x and y. So then we've got y equals 7x plus 5 over x minus 2. And that gives you your inverse function. So then you know that f to the negative 1 of x equals 7x plus 5 over x minus 2. All right, quadratic functions and models. So a quadratic function is a polynomial function of degree 2. So anything that's degree 2 is going to be a quadratic. And we're pretty familiar with what a quadratic looks like. This is standard or vertex form. So when you have a times x minus h squared plus k, you can find this by completing the square. And we'll go over that in just a second. But the vertex is going to be h comma k. So anything that's over here with your shifted, that's going to be your y value for the vertex. This is going to be your x value for the vertex. So remember, the parabola opens downward. If the coefficient out here is negative, then the parabola is going to open downwards. And if the coefficient is positive, then just like x squared, the parabola is going to open upwards. So that's going to come in handy later when we talk about maximum and minimum values. So we'll go over completing the square. So you can see here they've got f of x equals 2x squared minus 12x plus 13. So the first thing they do is factor 2 from the x terms. So we can we're trying to complete the square for these x terms on the inside. So we factor out the 2. So we're going to complete the square by adding 9 inside. And I'll go over a trick in just a second so it helps with completing the square. But anything that you add here, you're going to have to also subtract to keep the equation equivalent. So they've got, and you got to remember it's 2 times 9 that they're subtracting, because you've got a 2 out here that's multiplying everything inside the parentheses. So you can't just subtract 9. You got to subtract 2 times 9. So then you factor and simplify. So you've got this right here, x squared minus 6x plus 9 equals x minus 3 squared. And then you've got 13 minus 18 is negative 5. Quadratic function f is given. Express the function in standard form. Find the vertex and x and y intercepts of f. So we're given f of x equals 2x squared minus 20x plus 57. So we're going to factor out 2 from the x term so we can get that x squared by itself. So by completing the square, the best way to do this is to identify the linear coefficient, which is negative 10 right here. So this is your linear term. This is your quadratic term, because linear is dealing with just x alone. So identify the linear coefficient. It's negative 10. You're going to half it, which is negative 5, and then you're going to square it. That's how you know what to add to complete the square. So we halved it, we squared it, we got 25. So then we're going to add that 25 in here. So since we added 25, we have to subtract 2 times 25 because we've got that 2 outside here. We have to subtract whatever you add. Remember, whatever you add, you have to subtract the same amount to keep the equation equivalent. And be careful with the 2 outside of the parentheses. It's 2 times 25 that you have to subtract, not just 25. I'm going to sound like a broken record. But so then that gives us, we know we can factor this now, this x squared minus 10x plus 5. We know that's x minus 5 squared. So then we're going to just put it in those terms. So then we've got 2 times x minus 5 squared plus 57 minus 50 is 2 times x minus 5 squared plus 7. This is your standard in vertex form. So we know that the vertex equals 5, 7. I always just like to see whatever this equals to 0, then I know that's my, you know it's not negative 5. You know it's going to be positive 5 because I just put my x here. Whatever x has to equal right here. So the y-intercept, you know that from the original equation. The original equation right here told us that the y-intercept was plus 57. It's just like mx plus b. So then we use the quadratic formula on the original equation to find the x-intercepts. A equals 2, b equals negative 20, c equals 57. So you plug it all in here. X equals negative b plus and minus the square root of b to the second minus 4ac all over 2a. Hopefully everybody has that memorized pretty well from other classes. And then we notice that since after multiplying all this out, there are no x-intercepts because the radical is negative. When you have a negative radical after doing the quadratic equation, that means there's no real roots. That doesn't mean that there might not be some complex roots, but there have to be real roots for there to be x-intercepts. So if you ever get a negative radical for when you're trying to find x-intercepts, then that means there are no x-intercepts. It doesn't exist. There's no real roots. So showing this in vertex form, you can see it's the graph of x squared. We're just transforming the graph of x squared basically. So we're vertically stretching it by a factor of 2. We shifted it to the right 5 units and we shifted it up 7 units, just for what we learned from our transformations. So that's the vertex form. And we can see the vertex is at 5, 7 right here. The domain is negative infinity to infinity because it's stretching all the way, all these values over here to the negative infinity of x. And it's going to go all the way over here to the positive infinity of x. And then you can see that the range is going to include, because 7 is on the graph, it's going to include 7, and it's going to go up to positive infinity. Nothing down here exists for this graph. So we went over that already. All right, doing another one. F of x equals negative 4x squared minus 12x plus 1. Factor out a negative 4 from the x terms, so that gives us negative 4 times x squared plus 3x plus 1. To complete the square, we're going to identify the linear coefficient. So in this case, it's negative 3. That should have been a negative 3. Let's see. Identify the linear coefficient. Why is that not a... Hold on a second. Complete the square, identify the linear coefficient.
Is it because you took out a negative 4?
Yeah, it might be. I think so. Got the negative 4.
And that turns that to a positive 3x, right?
Yeah, it should be a 3. So then you're going to half it, and then you're going to square it. Yeah, that looks right. Yep. Okay, so same thing. Identify the linear coefficient, which is 3. You're going to half it, which is 3 halves, and then you're going to square it. So then that gives us x squared plus 3x plus 9 over 4 times negative 4 plus 1. And then we have to subtract the same thing that we added. Since we added a 9 over 4, it's negative 4 times 9 over 4 that we have to subtract. So, and this was something that I accidentally forgot to include in the one that I sent out. So I just made an edit here. I forgot to add the exponent here. So don't mind that. It's just something that I added for people that had the study guide beforehand. So we've got 1 minus a negative 9 because negative 4 times 9 over 4 is a negative 9. So then that puts us at -4 times x plus 3/2 squared plus 10. So you're basically just trying to complete the square so that you can factor this into an x plus whatever squared. So the vertex is going to be -3/2 comma 10. And the y-intercept from the original equation is +1. Using the quadratic formula to find the x-intercepts. So we've got a equals -4, b equals -12, and c equals 1. So we plug it all in here. And solving for x, we get x equals -3/2 plus or minus the square root of 10 over 2. I won't go through all of this just to kind of save some time. I'm pretty sure you guys know how to use the quadratic formula. So just anytime you're trying to find your x-intercepts, you're using the quadratic formula. So then we can see here, we've got -4x squared minus 12x plus 1. So we can see that our graph here, we've got -3/2 comma 10. That's our vertex. And if you wanted this, you can also see that it's the graph of -x squared, upside down parabola. And it's shifted to the left 3/2 units, and it's shifted up 10 units. So, and it's also stretched vertically by a factor of 4. All right. Moving on to maximum and minimum values. So if there's a positive coefficient, then it's a minimum value, because you think of the graph of x squared. So the graph of x squared has a positive coefficient, it's 1. So you're going to have a minimum value because the parabola is opening upwards. So if the leading coefficient is negative, parabola opens downwards, max value. So if you have a leading coefficient that's negative, then it's going to open downwards. That gives you a maximum value. Maximum or minimum value will be at the vertex. So the maximum or minimum value is the y value of the vertex, and it occurs at the x value. So that's something that's kind of the actual maximum or minimum value is the y value, and it occurs at the x value. So the vertex isn't the maximum or minimum value, and neither is the x value. But you can say that the max or min value is the y value that occurs at the x value. So if your vertex was 3, 4, then you would say that the maximum value was 4, and it occurs at x equals 3. So same thing right here, 3, 4. So you've got the minimum value is 4, and it occurs at x equals 3. Maximum or minimum value, you can also find it by using x equals -b over 2a. That's where it occurs. Remember, it occurs at the x. So you have to find the maximum or minimum value, you have to take the f of that. So it's going to be f of -b over 2a. So this equation saves time, so you don't have to put the equation into standard form or vertex form when given a quadratic equation, but either one will work. So if you wanted to do it the other way and try to put it into vertex form to find out what the vertex was, then that'll work too. But you can also just do this to save time. So anytime you're given maximum or minimum value, just remember -b over 2a. And that's, so you're going to find that first. So start by finding the x value at which the max or min occurs, and then plug in the x value into the original function to find the y value. So find the maximum or minimum value of the function. So you're given f of t equals -3 plus 80t minus 20t squared. You want to rearrange this a little bit so you can get it into that quadratic form there. So it's going to be -20t squared plus 80t minus 3. So you've got a equals -20 and b equals 80. So that you want to make sure you put it in this form so that you know exactly what your a, your b, and your c are going to be. But we only need a and b for this. So x equals -b over 2a. Since b equals 80, it's going to be -80 over 2 times -20. So you've got -80 over -40, which is 2 over 1, which is 2. So now that you know it occurs at x equals 2, we've only found x so far. So we've got to plug in what we found, x equals 2, into the whole function that we were given so that we can find the y value at which the maximum or minimum occurs. So you're going to take f of 2, which is -20 times 2 squared plus 80 times 2 minus 3. And that equals -20 times 4 plus 160 minus 3. So that gives us -80 plus 157, which equals 77. So the vertex we now know is 2, 77. And the maximum value is 77. And it occurs at x equals 2. All right, polynomial functions and their graphs. So this is just basically the layout of a polynomial function. You've got right here, 3 is your leading coefficient. The leading term is 3x to the 5th. It's a 5th degree polynomial because the highest degree of the leading term, the polynomial is going to have the same degree as the degree of its highest degree term. So we've got, this is a 5th degree polynomial. These are all coefficients, including your constant term here. Constant is the one that doesn't have any x value on it. So we're going to talk about end behaviors a little bit here. So I've got a good way to remember end behaviors because you're not going to be able to have something like this to look at when you're taking the exam. So, but just basically anything with an even degree that has a positive coefficient is going to look just like the graph of x squared. So with end behavior, you've got x approaches infinity as f of x approaches infinity. So as x approaches infinity, you can see that the y right here is also approaching infinity. And as x approaches negative infinity, we can see that the y value is also approaching infinity. So over here, if you have a positive leading coefficient in an odd degree, it's going to be just like the cube function. So the end behavior, as x approaches infinity, we see that y also approaches infinity. As x approaches negative infinity, we see that y approaches negative infinity. And then they're opposites for here. But here, we'll go ahead and go into it this way. This is an easier way to remember it. So to remember end behaviors, think of the graphs of x squared and x to the third. So x squared has a positive leading coefficient, which is, pretty sure everybody knows what the graph of x squared looks like. It's just a parabola that opens upwards. So, and it's also an even degree. So if you can remember anytime any equation that you're given, if it has a positive leading coefficient and an even degree, it's going to be the same end behavior as this parabola that opens upwards. So f of x equals negative x squared. So this is basically just reflected. Remember, we're affecting the y values, so we're going to reflect it on the x-axis. So negative x squared has a negative leading coefficient, which is -1, and it is an even degree, and it's the graph of x squared reflected about the x-axis, and there's a parabola that opens downwards. So anything that has a negative leading coefficient and an even degree is going to have the same end behavior as this graph right here. And f of x equals x cubed has a positive leading coefficient, is an odd degree. This is the cube function. So anything that has an odd degree and a positive leading coefficient, you're going to have your end behavior that's going to look like this. And then it's switched over here. It's reflected about the x-axis. So f of negative x cubed has a negative leading coefficient. -1 is an odd degree and is the graph of x to the 3 reflected about the x-axis. Basically, it just helps to know what the end behaviors will be for other functions with odd or even degrees and positive or negative leading coefficients. If you can remember these graphs, then you can figure it out for any degree polynomial, whether it has a positive or negative leading coefficient. You can figure out what the end behavior will be if you can remember these ones. Just remember if it's negative or positive and if it's odd or even. So determine the end behaviors of the following functions. So we're given that p of x equals 2x to the third minus x squared minus 18x plus 9. So it has a positive leading coefficient of 2 and it has an odd degree of 3. So the end behavior will be like the cube function. Remember we saw the cube function right up here. It has a positive leading coefficient and an odd degree. So we know that it's going to be right up here and going down in the other direction. So you can see y approaches infinity as x approaches infinity. See, as x approaches infinity this way, you've got y is approaching infinity, and as x approaches negative infinity, you've got y approaching negative infinity. So that's what the graph looks like. So you got q of x equals negative x squared times x squared minus 4. Sometimes you have to multiply these out to see and just make sure if it's negative leading coefficient and an even degree. So it is, we've got negative x to the 4th plus 4x squared. End behavior will be like the graph of negative x squared. Remember, it's just like the upside down parabola because we've got negative x squared. So it just helps with remembering end behaviors. All right, moving on to real zeros of polynomials. If p is a polynomial and c is a real number, then the following are equivalent. C is a zero of p, x equals c is a solution of the equation p of x equals 0. X minus c is a factor of p of x, and c is an x-intercept of the graph of p. Basically, factoring a polynomial gives you the zeros, which are the x-intercepts. That's what this is saying. X equals c is a solution. So we'll move on to this. Let's see, intermediate value theorem for polynomials. I don't think this is super important to know. It can be probably helpful, but it's basically saying that if p of a and p of b have opposite signs, so say that p of a is a negative, say a is a negative number, or p of a is a negative number and p of b equals a negative number, they're just saying that there's going to be one zero in between those two values. So I haven't really found it particularly helpful though. Guidelines for graphing polynomial functions. So zeros, factor the polynomial to find all its zeros, and these are the x-intercepts of the graph. Test points, make a table of values for the polynomial, include test points to determine whether the graph of the polynomial lies above or below the x-axis on the intervals determined by the zeros, include the y-intercept in the table. Determine the end behavior, and then graph. Plot the intercepts and other points you found in the table, sketch a smooth curve that passes through these points and exhibits the required end behavior. So basically, we'll go through this, how to graph it, how to sketch a graph, because we might be given some graphs or whatever to identify which one to choose from for the equation. But you don't really have to do all the test points to figure out the general shape of the graph. If you can get the intercepts and you can get the end behavior, then you can pretty much figure out what the graph is going to look like. Another thing that's important to know is knowing the multiplicities of the zeros. So if the multiplicity of a zero, like you've said that you've been given like 1 is a zero of multiplicity 2, that means that 1 is a zero twice. So basically, if it's an even multiplicity, so if 1 has a multiplicity of 2, then it's going to bounce off of the x-axis. If the multiplicity of the zero is odd, then it's going to cross the x-axis at C. So if you're given that 1 is a multiplicity of 1, then it's going to cross at 1. And if you're given that 1 is a multiplicity of 2, then it's going to bounce off the x-axis at 1. Factor the polynomial and use the factored form to find the zeros, then sketch the graph. So we're given that p of x equals negative x to the third plus x squared plus 12x. So we're going to factor out a negative x. That gives us x squared minus x minus 12, which can be factored to x minus 4 times x minus 3, so that we know now our zeros are 0, 4, and negative 3, because those all equal 0. So these are going to be your x-intercepts, and they all have multiplicity 1 because they've only occurred one time. So they're all going to cross the x-axis at those x-intercepts. So you're going to determine the end behavior. Since it's a negative, it's negative and it's an odd degree, it's going to be just like, let's see, where do we have it here? Since it's negative and it's an odd degree, the end behavior is going to look like this. Just like the opposite of the cube function. Let me get back to it. I try not to backtrack too much. All right, so start by marking the end behavior and the x-intercepts. So we know that that's what our end behavior is going to look like according to the coefficient and the odd degree. So we know our end behavior. So then we've got, what were our zeros again? 0, 4, and negative 3. So we've got negative 4, 0, and 3. So once we've got those marked, that really gives you enough to know, since you know it's going to cross through here and it's going to cross again and it's going to cross through one more time. You can pretty much already, you don't have to really do the test values, but if you wanted to be more accurate and actually graph the function, then you can start plugging in some values. So you can start seeing what the graph is going to do when x equals 3. So we're going to take f of 3. So we do f of 3, and that gives us 18, so that we know a point on the graph is going to be 3, 18. So I just plugged in some values here and just did it for everything to give an idea of the test values. But really, you don't have to do this. You don't have to do the test values. You can figure out, as long as you know, if you know the end behavior, you know the x-intercepts, the y-intercept, then you know, and you know when it's going to cross or bounce off of the x-axis, then you can figure out exactly what the graph looks like. It might not look exactly like the graph without the test points, but if you do the test points, then you're going to get a graph like this. So then you connect the graph going through each x-intercept. So it goes through, and it's got the same end behavior. So we know we did it right. All right, local maxima and local minima of polynomials. They're also called local extrema. So we're pretty familiar with local maximum points and local minimum points. That's what those look like. So for a polynomial function, the number of local extrema must be less than a degree, as the following principle indicates. So at the most, a polynomial will have n-1 local extrema. So if a graph has 2 local maxima and 1 local minima, it has 3 local extrema. So the polynomial must be at least degree 4, because we know that since it's degree 4, there's going to be 4 minus 1 local extrema at most. It could have less than that. So you know that there will be at most less than the degree of polynomial. If the polynomial is degree 5, then there are at most 4 local extrema. There may be less than 4. The graph is what determines how many. So note how many local extrema the polynomial will have at most, which is n-1. Factor the polynomial to find the zeros, determine the end behavior according to the leading coefficient and degree, and sketch a rough graph to determine how many local extrema there are. So here's a couple of examples. Graph the polynomial and determine how many local maxima and minima it has. So you've got y equals x to the fourth minus 5x squared plus 4. Polynomial will have at most 3 local extrema, because remember, it's 4 minus 1. So we start by factoring. You might need to use synthetic division. So with synthetic division, by factoring, we're going to take the factors of the constant term over the factors of the leading coefficient of the beginning term. So it's going to be the factors of 4 over the factors of 1, which gives us plus and minus 1, plus and minus 2, and plus and minus 4. So we're going to try some of those, starting with 1. We're going to see if it's a factor. So we got a remainder 0 here for the factoring. So that means 1 is a factor. So that gives us x minus 1, and then times x to the 1x to the third times 1x to the second minus 4x minus 4. So then factoring further, we'll try -1. So we just take all these leading coefficients here. We've got 1x to the third, 1x squared minus 4x minus 4. And then we're going to do synthetic division with these, and we get a remainder 0. So now we know that we've got x minus 1 times x plus 1, since they're both factors. And that leaves us with x squared plus 0x minus 4. So it's x squared minus 4. So we notice that x squared minus 4 is a difference of squares. So that can be further factored to x minus 1 times x plus 1 times x minus 2 times x plus 2. So all the x-intercepts are going to be 1, -1, 2, and -2. And they all have a multiplicity of 1. So at each one of those x-intercepts, the graph's going to cross. The end behavior will be like the graph of x squared, because we've got an even leading coefficient, or excuse me, a positive leading coefficient in an even degree. So that's just like x squared. So we know it's going to look like that upwards facing parabola. The end behavior, let's see, y-intercept is 0, 4, because we were given that from the original equation. So with all this information, we can graph what it looks like, marking our x-intercepts, marking our y-intercept, and got the end behavior. So then we go through, and we've got 2 local minima right here and 1 local maximum. So it's got 3 local extrema. All right, a polynomial function will sometimes have less than n-1 local extrema. It's just saying that it's going to be at most n-1. So we've got 7x to the fourth plus 3x squared minus 10x. First thing we're going to do is factor out an x. So we already know that 0 is a factor by factoring out an x. So then we're going to take the factors of -10. So we can get that constant term. We've got factors of -10 over the factors of 7. And getting all this, we've got all of these factors, all these possible rational roots here. So we just start trying them. We're going to start trying it with 1. So we find out that 1 is a factor. So then we got x times x minus 1 times the 7x squared plus 7x plus 10. And then we're going to do the quadratic formula, since we can't easily factor this. So we've got a equals 7, b equals 7, c equals 10. Plug it into the quadratic formula. There's no other real zeros, because this is a negative radical right here after we do the quadratic formula. So we know that our x-intercepts from this original equation is going to be 0, because we've got a 0 out here and 1. So the end behavior is going to be like the graph of x squared, and the y-intercept is 0, 0. We've got that from the original equation. So then we can graph it. We've got 1 local extremum, a local minimum. That's the only 2 x-intercepts that we had. So even though it's a degree 4, sometimes it'll have less than 3 local extrema. All right, dividing polynomials. This is from 3.3 of the textbook. All right, so we've got p of x over d. These are 2 different forms that you can basically write your answers in. Sometimes you're asked for p of x, sometimes you're asked for p of x over d of x. So the only time, be able to write them both ways. The only time the remainder goes over the divisor is with p of x over d of x. So sometimes it's kind of confusing to remember when to put the remainder over the divisor, but that's only if you're asked for p of x over d of x. So when you've got the whole thing divided by the divisor equals the quotient plus the remainder over the divisor. Or you've just got the dividend equals the divisor times the quotient plus the remainder. So this is just some long division here. So you're taking this x and dividing it into this first term here. So x goes into 6x squared. It goes in 6x times. So then you're taking 6x times x minus 4, which is 6x squared minus 24x. And we're subtracting all of that from 6x squared minus 26x. So that gives us a -2x. We drop down the 12. So then we're going to take x and try to go into the negative 2x, x goes into negative 2x negative 2 times. So then negative 2 times x minus 4 is negative 2x plus 8. So then we're going to do negative 2x plus 12 minus negative 2x plus 8, which equals 4. So that's our remainder. All right, and then those are the two different ways to write this. We've got the p of x over d of x equals the quotient times the remainder over the divisor. Or we can write it this way, the dividend equals the divisor times the quotient plus the remainder. So if you're just asked for the dividend, then the remainder doesn't need to go over the divisor. That's only if the dividend is over the divisor. Find the quotient and remainder using long division. So we've got 6x to the third plus 2x squared plus 22x. 2x squared plus 5. Something that I found is kind of helpful sometimes is writing in values, even if you don't have them for basically, like right here, we don't have an x squared value. So let's go ahead and try it. We'll do, how many times does 2x squared go into 6x to the third? It goes in 3x times. So we're going to take 3x times 2x squared plus 5, which gives us 6x to the third plus 15x. So just to keep everything in order, since I don't have an x squared term here, I just wrote a 0x squared here. So we've got 6x to the third plus 0x squared plus 15x. So it's just going to be 6x to the third minus 6x to the third, and it's going to be 22x minus 15x. So, and then you remember that you've got this 2x squared left over right here. So you've got 2x squared plus 7x, and then you can bring down the 0 or add a 0. I just do that because it's kind of helpful sometimes just to keep everything in order. So then you've got this 2x squared plus 7x. So how many times does 2x squared go into 2x squared? It goes in 1 time. 1 times 2x squared plus 5 is going to be 2x squared plus 5. And then you just subtract them here. So you've got 2x squared plus 7x minus 2x squared plus 5. So 7x minus, or 2x squared minus 2x squared is 0. Then you've got 7x minus 0x is 7x. And then you've got 0 minus a positive 5 is negative 5. So that's going to be your remainder there. So the quotient is 3x plus 1. The remainder is 7x minus 5. So you can write it these two different ways. You can do it with the dividend, and you can do it with the dividend over the divisor. That's when you have to put the remainder over the divisor. All right, synthetic division. So you can use synthetic division when the divisor is in the form x minus c. If it's not in the form x minus c, if it's not just a single x, it won't work. It won't work if we have something like this. We can't use synthetic division with 2x squared plus 5. It has to be in the form x minus c. So just something to remember. So when doing synthetic division, the first thing we're going to do is take all the coefficients and put them up here. And then we're going to take our factor and we're going to drop down this 2. We go 3 times 2 is 6. Then you're going to add. So negative 7 plus 6 is negative 1. So then you go 3 times negative 1 is negative 3. 0 plus negative 3 is negative 3. 3 times negative 3 is negative 9. 5 plus negative 9 is negative 4. That's your remainder. So it kind of shows the relation between long division and synthetic division, where everything goes. But let's see, this is just explaining more synthetic division. Hopefully you guys are pretty comfortable with synthetic division. Remember to use zeros as placeholders for x term coefficients that aren't included in your dividend. So find the quotient and remainder using synthetic division. We've got x to the 5th plus 3x to the 3rd minus 6 over x minus 1. So since it's in the form x minus c, then we know that c is going to be 1. So we've got the coefficients for the dividend will be 1, 0, 3, 0, 0, and negative 6. Because there is no x to the 4th term, and there's no x squared term, and no x term. So we have to write in zeros for them. So it's going to be 1x to the 5th plus 0x to the 4th plus 3x to the 3rd plus 0x to the 2nd plus 0x minus 6. So that's the same thing here. Just got to remember to write in your zeros, or else that can kind of mess up the equation. So bringing down our 1, 1 times 1 is 1, 0 plus 1 is 1, 1 times 1 is 1, 3 plus 1 is 4, 1 times 4 is 4, 0 plus 4 is 4, 1 times 4 is 4, 0 plus 4 is 4, 1 times 4 is 4, negative 6 plus 4 is negative 2. So that gives us this quotient here. I usually like to circle my remainder just so I can know where the equation kind of ends. I know my constant term is going to be 4. It just makes it easier for me to write when I'm writing it down on paper. If the remainder is 0, then c is a 0 of p of x, and x minus c is a factor of p of x. So anytime you get a remainder that's 0, that means this is going to be a 0. All right, so the remainder theorem, I don't really know if we're gonna ever have to use this, but it's just kind of cool, I guess, knowing if the polynomial p of x is divided by x minus c, then the remainder is the value p of c. So it's basically saying, so if we took the same one that we had, p of x equals x to the fifth plus x to the third minus 6, and then we took p of 1, so it's saying that if we took the 0, if p of x is divided by x minus c, then the remainder is the value p of c. So we've got x minus 1. So if we did p of 1, then that's going to give us the remainder. I don't really know if that's going to be helpful for the exam, but basically I guess I don't even know why they included it, but it's there. Finding a polynomial with specified zeros. So find a polynomial of the specified degree that satisfies the given conditions. So we're supposed to find a polynomial that's degree 4, and the zeros are -2, 0, 1, and 3. And the coefficient of x to the third is 4. So we can go ahead and write this by listing all zeros in the form x minus c. So we've got x plus 2, which is this -2 here. So that's going to equal 0. And then we've got the 0 on the outside. We've got x minus 1 here, and we've got x minus 3. So we're just going to list all of those zeros in the form x minus c. And then we're going to expand the equation in pieces. So the first thing we're going to do is multiply x plus 2 and x minus 1 together to give us x squared plus x minus 2. So then we can multiply these two together. We've got x squared plus x minus 2 times x minus 3, which gives us x to the third minus 3x squared plus x squared minus 3x minus 2x plus 6. And then simplifying it out, we've got x to the third minus 2x squared minus 5x plus 6. And then we're just going to multiply that x and distribute it. So that gives us x to the fourth minus 2x to the 3 minus 5x squared plus 6. But it says that the leading coefficient of x to the third must be 4. So what can you multiply the whole equation by to get 4 as the leading coefficient? You must multiply the whole equation to keep it equivalent. So it's saying that this x to the third term needs to equal 4. So we can multiply everything by -2 to get that to equal 4. So we multiply everything by -2. That gives us -2x to the fourth plus 4x to the third plus 10x squared minus 12x. And now the leading coefficient of x to the third is 4. So here's another one. The degree is 4. The zeros are -1, 1, and square root of 2. And we need integer coefficients and a constant term of 6. So since you need a degree 4 and integer coefficients, negative square root of 2 will also be a 0. You have to have another 0 to make it degree 4, and multiplying the square root of 2 by the negative square root of 2 will give you integer coefficients. So this is the way we're going to write it. We're going to write all the zeros in the form x minus c. So we've got x plus 1 times x minus 1 times x minus the square root of 2 times x plus the square root of 2. So multiplying that out, we've got x squared minus 1 times x squared minus 2, and both are a difference of squares. So multiplying them together, we get x to the fourth minus 2x squared minus x squared plus 2, which gives us x to the fourth minus 3x squared plus 2. So we've got integer coefficients, but you need a constant term of 6. So what can you multiply the whole equation by? Well, we can multiply it by 3 to get 6. So we've got 3 times x to the fourth minus 3x squared plus 2, which gives us 3x to the fourth minus 9x squared plus 6. So now we've got all integer coefficients and a constant term of 6. So irrational roots occur in conjugate pairs, just like complex zeros. So if a minus the square root of b is a factor, then so is a plus the square root of b. So if the square root of b is a 0, then so is the negative square root of b, just like we saw up here. They only gave us the square root of 2. But since we know it's just like complex zeros, they occur in conjugate pairs. So we also know that negative square root of 2 will also be a 0. They'll do that a lot. They'll only give you 3, and then it'll tell you that it's supposed to be a 4th degree polynomial, but even though they only gave you 3. So you know to start looking for a conjugate when you have less zeros than what was given for the degree. Okay. Real zeros of polynomials. All right, so consider the polynomial in factored form. P of x equals x to the third, x minus 3 times x plus 2 times x minus 4. When expanded, it is p of x equals x to the third minus 5x squared minus 2x plus 24. The zeros of p are 3, -2, and 4. When expanded, the constant 24 is obtained by multiplying -3 times 2 times -4. This means that the zeros of the polynomial are all factors of the constant term. The rational zeros theorem generalizes this observation. So it's basically saying that when you take all of these zeros, and you multiply them all together, 3 times negative 3 times 2 times negative 4, then it's going to give you 24. So let's see here, rational zeros theorem. So this is basically saying, this is when we take to find all the rational or possible zeros, take the factors of the constant term over the factors of the leading coefficient. So that's what we do when we're doing synthetic division. So finding the rational zeros of a polynomial, you list all the possible zeros using the rational zeros theorem. So you're taking the constant over the factors of the leading coefficient. And then you're going to use synthetic division, and you're going to try some of the candidates for the rational zeros. So you're just going to try some of the possible zeros to try to see if the remainder is going to be 0. If you find a remainder 0, then you know it is a 0. So it's going to be a rational root. So then just keep going until you reach a quotient that is a quadratic or factors easily, and then use the quadratic formula to find the remaining zeros. So it says find all rational zeros of the polynomial, write the polynomial in factored form. So we're going to take the factors of the constant term over the factors of the leading coefficient. So we've got the factors of -4 over the factors of 2, which is going to give us all of these combinations here, which gives us plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 1 over 2. So these two canceled out because we don't have to list them twice, because 2 over 2 is the same thing as 1 over 1. They both equal 1. And 4 over 2 is the same thing as 2 over 1. So I highlighted those, just showing that they don't really need to be included, but you can write them all out like that. So then you start trying some of the possible zeros with synthetic division. The best way to do is just start with the smallest positive value and work your way up, or whatever works for you. If you want to start with the smallest negative values, but you just try possible zeros until you get 0 as the remainder. I just like to go in order so I don't start jumping around and miss ones that I've already gone over or something like that. So we've got 1, 2, and 4 and half that are possible rational roots. So I start with 1. So we do synthetic division, we find out that we have a remainder of 2, so that's not a root. So then we're going to move on to 2, and we do synthetic division, and we found out that it has a remainder 0. So then we're going to write it in the form x minus c with the quotient. So we've got x minus 2, and then we've got 2x to the third minus 3x squared minus 3x plus 2. So since you already know 1 is not a 0, you don't need to try it again. Once you find out that something is not a 0, you don't have to keep trying it in this quotient. So I've already found out that 1 is not a 0, so I don't have to try it again. So try using synthetic division again with the quotient until you get a quadratic, which is a degree 2 polynomial. And to find the remaining zeros, the quadratic will either be easily factorable, or you'll need to use the quadratic equation if it isn't easily factorable. So I just started with -1. So we take all of these leading coefficients here and then put them right here. We're going to do it with synthetic division. And we find out that -1 is a 0 because it has a remainder 0. So write it in the form x minus c with the quotient and the factor you found before. So we're building on it. We've got x minus 2 that we found before times x plus 1 times 2x squared minus 5x plus 2. And notice that this quadratic can be factored. So we can factor this one. So x minus 2 times x plus 1 times 2x squared minus 5x plus 2 equals x minus 2 times x plus 1 times 2x minus 1 times x minus 2. So we've got x minus 2 in there twice, so we can just say x minus 2 squared times x plus 1 times 2x minus 1. This is factored form. So we know that the zeros are 2. We've got 2 as a multiplicity 2 because it occurs twice. And then we've got -1, and we've got 1/2 because 2 times 1/2 minus 1 is 0. Find all the real zeros of the polynomial, use the quadratic formula if necessary. So this is one that doesn't really factor easily. But same thing, we're going to take the factors of the constant term over the factors of the leading coefficient. So we know that our possible roots are going to be plus or minus 1, plus or minus 1/2. So we're going to just start trying them with 1. So we see 1 give us a way too high of a remainder. So sometimes I like to go in the negative direction. If I see that I have a really positive remainder here, I might want to go in the negative direction with my possible roots. So we're going to try -1, and we find out that we have a remainder of 0. Since it's -1 is a 0, write it in the form x minus c with the quotient. So we've got x plus 1 times 2x minus 3 plus 13x squared plus 4x minus 1. So since you already know 1 is not a 0 because it has a remainder of 36, you don't need to try it again. So we're going to start with -1/2. We'll try -1/2. So then we're going to try to divide -1/2 into this. So then we've got, it is a 0. And then so we've got x plus 1 times x plus 1/2 times 2x squared plus 12x minus 2. So you can factor out 2 from the last factor and multiply it into the second factor. This is if you're trying to completely factor appropriately. So you can, this becomes, if we factor out a 2, this becomes x squared plus 6x minus 1. So then we take that 2 and we multiply it into x plus 1/2, which gives us 2x plus 1. This is only if you're trying to, you can still find all the roots without doing that, because these two will actually have the same roots. This 2x squared plus 12x minus 2 has the same roots as this. So I wouldn't really pay too much attention to that. We probably won't be asked to factor out a 2 and then multiply it into the second factor, but just for the sake of keeping it equivalent and knowing how to actually fully factor it, that's why I did that. But then we can use the quadratic formula on this quadratic, x squared plus 6x minus 1. So plugging everything in here with a equals 1, b equals 6, and c equals -1, then we get x equals -3 plus or minus the square root of 10. So the zeros are -1, -1/2, and -3 plus the square root of 10, and -3 minus the square root of 10. So you can write it like this. You can just plug them all in to x minus c. So really when you're doing x minus c, you're just going to plug in that value into parentheses. So you can say x plus 1 times 2x plus 1 times x minus a -3 plus square root of 10 times x minus a -3 minus the square root of 10. So when you do that, you can see that the complete factored form says x minus a -3 is x plus 3. And x minus a positive square root of 10 is minus square root of 10. So it looks like this. So then you've got x minus a -3 minus the square root of 10. So you've got x plus 3 plus a square root of 10, because x minus a negative square root of 10 is x plus square root of 10. So Descartes' rule of signs, let P be a polynomial with real coefficients. The number of positive zeros of P of X either is equal to the number of variations in sign in P of X or less than that by an even whole number. And the number of negative real zeros of P of X is either equal to the number of variations in sign of P of negative X or less than that by an even whole number. So we'll go over this in just a second. So variations in sign are counted this way. So you're just going to start with, if this is positive, 5x to the 7th is positive. So we've got positive to a negative. That's one variation sign. We've got negative to a negative. That hasn't changed. So we've got negative to a positive. That's another variation in sign. So we've got positive to a positive. That's not a variation in signs. And then we've got positive to a negative, which is another variation in sign. So total, this has 3 variations in sign. And that's for P of X. P of X is what is given. So right here, we can see P of X has 1 variation in sign, because we're going from positive 3x to the 6th to positive 4x to the 5th. So that hasn't changed. So we're going from positive 4x to the 5th to positive 3x to the 3rd. That hasn't changed. So then we're going positive 3x to the 3rd to negative x. So there's a variation in sign right there. And then we're going negative x to -3. There's no variation in sign. So there's 1 variation in sign total for P of X. So that means it has exactly 1 positive 0, because it can either be equal to the number of variations in sign, or it can be less than that by an even whole number. So it has to be less than that by an even whole number, like 2, for example. But since it's 1, it has exactly 1 positive 0. So for P of negative X, you're going to plug in negative X for all of the X's and then count variations in sign for the number of negative real zeros. So to find the number of negative real zeros, we've got to do P of negative X. So like I said, we're going to just take this P of X, we're going to plug in a negative X there. And then everywhere we see X in this original equation for P of X, we're going to plug in a negative X. So it gives 3x to the 6th minus 4x to the 5th minus 3x to the 3rd plus x minus 3. So we've got anything negative raised to an even power is going to be positive. So we've got 3x to the 6th. Then we've got anything raised to an odd power that is negative is going to be negative. So we've got negative 4x to the 5th. And anything raised to an odd power that is negative is going to be negative. So we've got negative 3x to the 3rd. And then negative minus a negative x is positive, and then minus a 3. So then we're going to positive 3x to the 3rd to negative 4x to the 5th. There's 1 variation in sign. A negative to negative, there's not a variation there. So we've got negative to positive, there's another variation, and we got positive to negative. So P of negative x has 3 variations in sign. So P of x either has 3 or 1 negative real zeros, because since there's 3 variation in signs, it can either be 3, it can be equal to the number of variation in signs, or it can be less than that by an even whole number. So it can be less than that by 2. So it can be 3 or 1 negative real zeros. So that makes a total of either 2 or 4 real zeros, both positive and negative, because since we had 1 positive 0 from P of x, and we have either 3 or 1 negative real zeros, and we add 1 to that for the positive, then we have either 4 or 2 real zeros. Descartes' rule of signs is a little bit difficult at first, but it's really just, as long as you remember to plug in the P of negative x and put the negative x everywhere, that's how you find the negative real zeros. It's really just telling you how many there's going to be. I don't really think it's going to be that necessary, but I guess in case you get a question like that, I just really don't see them putting anything about Descartes' rule of signs on there, but it's, I guess, helpful to know. The upper and lower bounds theorem. So let P be a polynomial with real coefficients. If we divide P of x by x minus b with b is greater than 0. So there's an easier way to say this, this rule right here. So the upper bound is if the quotient and the remainder have no negative entries. And you're doing this by basically going up in integers from 0 for the upper bound and going down in integers from 0 on the negative side for the lower bound. So 0 can be either considered non-positive or non-negative in these cases. So when you're looking for an upper bound, you want to make sure that after you do synthetic division, you have all non-negative entries. So that's going to be an upper bound. And if they alternate in sign, then you have a lower bound. So you've got 1 to a negative 3, 6, negative 16, and 43. They all alternate positive to negative. So these, even though this is a 0, these still alternate all positive and negative. That's what they mean by 0 can be considered either non-positive or non-negative. So you've got 1 to a possible non-positive, so that can be considered negative, to a positive, to a negative, to a positive. So that can also be considered a lower bound because it has alternating non-positive and non-negative numbers. So basically, just for the upper bounds and the lower bounds, you're just going to try integers. They don't have to be factors. They don't have to be any of the possible ones. That's what kind of confused me a little bit at first, was I was trying to find upper and lower bounds within the factors. But just start trying integers greater than 0. Start with 1, start with 2, start with 3, 4. Just go up from 1, 2, 3, 4 on all these integers for an upper bound until you get those non-negative or non-positive entries in your synthetic division. Try integers less than 0 for the lower bound. So you're going to try -1, -2, -3 until you find all those alternating non-positive and non-negative entries. So the upper and lower bound integers, they can't be factors. So the remainder can't be 0. If you're just trying to find what numbers all the zeros lie between. So we'll kind of go into this. So find the integers for the upper and lower bounds for the real zeros of the polynomial. So if we're given P of x equals x to the third minus 3x squared plus 4, start just trying synthetic division with integers that are less than 0 for the lower bound. So we'll start with -1. So then we try -1 into synthetic division for this, and then we see that -1 can't be a lower bound because it is a 0. So remember, lower and upper bounds, they can't be zeros. So if you have a remainder 0, you need to keep going. So then we're going to try -2. So we try -2, and we see that we've got a positive, a negative, a positive, and a negative. So -2 is the first integer where the signs alternate positive to negative, and it isn't a 0. So -2 is the lower bound. So now we find the upper bound by trying synthetic division with integers greater than 0. So we'll start with 1. So 1, for an upper bound, we need all positive entries for our synthetic division. So we already see we have some negatives here. So 1 isn't an upper bound. So we try 2, and we see that 2 is a 0. So 2 can't be an upper bound. So all the signs are not positive, so it also can't be an upper bound. So then we're going to keep going. We go with 3. And then we see that this is the first integer where we have all positive entries. And because 0 can be considered non-negative, so all the signs are non-negative, so that therefore 3 is an upper bound. So just try integers greater than 0 for the upper bound and try integers less than 0 for the lower bound. And just a reminder, a polynomial has no real zeros if all the possible rational zeros have remainders. So irrational roots occur in conjugate pairs, just like complex zeros. I think we already went over this. So just remember, if the square root of something is a 0, then so is the negative square root of something. It's just like complex conjugates when we're talking about complex numbers, which we're going to go into next. We've got complex numbers. So a complex number is just a plus bi. And always remember that I squared equals -1. A is the real part right here. This is your real part of the number, and B is your imaginary part. All numbers can be written as complex numbers. Every single number can be written as a plus bi. A complex number with the imaginary part 0 is just a real number. So if we've got 1 plus 0i, that equals 1. And then, so we can write 1 as a complex number. Complex with the real part 0 is called a pure imaginary number. So if we've got a real part 0 and we've got an imaginary part 2, we've got 0 plus 2i, that just equals 2i, and 2i is a pure imaginary number. Adding, subtracting, and multiplying complex numbers. So you can either remember these equations, which I found super difficult. It would be awesome if I could just remember these and just do it in my head that way. But you can just add and subtract the real and imaginary parts. And multiplication is just like multiplying binomials, but you always have to remember that I squared equals -1. So evaluating the sum or difference and write the result in the form a plus bi. So we've got -12 plus 8i minus 7 plus 4i. So we're just going to take these real parts right here and subtract them from each other. And we're going to take the imaginary parts and subtract them from each other. So we've got -12 minus 7 plus 8 minus 4i. So then that gives us a -19 plus 4i. So we've got -6 plus i plus a 9 minus I. So we're going to take the real parts and add them, and then we're going to take the imaginary parts and add them. So we're going to have -6 plus 9, and we're going to have positive 6i plus a -i, which gives us 3 plus 5i. So evaluate the product and write the result in the form a plus bi. So we've got 7 minus i times 4 plus 2i. So we've got 7 times 4 is 28. We're just distributing here. 7 times 4 is 28. 7 times 2i is 14i. Then we've got -i times 4 is -4i. Then we've got -i times 2i is -2i squared. So you're just multiplying it like binomials. And then you just remember that I squared equals -1. So then we're going to simplify this further. We've got 28 plus 10i because 14i minus 4i is 10. And then we've got -2 times the -1 because I squared equals -1. So this is the same thing as saying 28 plus 10i minus a -2, or 28 plus 10i plus 2, which is 30 plus 10i, because 28 plus 2 is 30. All right, complex conjugates. So a complex conjugate is written as like Z bar is the right way to, I guess, denote a complex conjugate. But multiplying a complex number by its complex conjugate gets rid of the imaginary part. And it is always a non-negative real number. So if you multiply 1 minus I times 1 plus I, there's going to be no imaginary part. Same thing if you multiply 3 plus 2I times 3 minus 2I, it's just going to be a squared plus b squared. This is kind of easier to remember. So if you can remember this equation, then that's good. But you can always just multiply them together, and then you'll see that they cancel out. Just like a difference of squares. It's exactly the same as a difference of squares. All right, dividing complex numbers. To simplify the quotient a plus bi over c plus di, you multiply the numerator and the denominator by the complex conjugate of the denominator. So just take the complex conjugate of the denominator, and you're going to multiply that by the complex conjugate over itself. So if we got c plus di in the denominator, then we're going to multiply it by c minus di over c minus di. So we'll just try one real quick. Evaluate the quotient and write the result in the form a plus bi. So we've got 10i over 1 minus 2i. So we know that we're going to have to multiply it by 1 plus 2i over 1 plus 2i. And then you can multiply fractions. With fractions, you multiply across. So we've got 10i times 1 plus 2i, which gives us 10i plus 20i squared. And then we've got 1 minus 2i times 1 plus 2i, which gives us 1 plus 2i minus 2i minus 4i squared. So you can see these two cancel out. So then we've got 10i plus 20 times, remember I squared is -1, so we've got 20 times -1. So then we've got 1 minus 4 times -1 because we've got 4i squared, and I squared is -1. So then we've got -20 plus 10i, and 1 minus -4. So that gives us -20 plus 10i over 5. Dividing everything by 5, we get -4 plus 2i. Square roots of negative numbers. The principal square root of -r is I square root of r. So you're just basically popping out that I every time you see a negative sign. You just, I comes outside of the radical. So evaluate the radical expression, the square root of -3 times the square root of -12. So that equals I square root of 3 times I square root of 12. So you're just taking that negative, the negative just pops outside of the radical and it becomes I, because I is the square root of -1. So we've got, multiplying them together, you get I squared times the square root of 3 times 12, which is I squared times the square root of 36, which is I squared times 6, which is -1 times 6, which is -6. So then here's another one, 2 plus the negative square root of 8 divided by 1 plus the square root of -2. So we've got 2 plus I squared of 8 over 1 plus I squared of 2. And then you've got 2 plus I squared of 4 times 2. We can pop out this square root of 4 outside of the radical to make it 2i. So then we've got 2 plus 2i square root of 2 over 1 plus I square root of 2. And then we can factor out a 2 here on the top, and we see that 2 times 1 plus I square root of 2 over 1 plus I square root of 2 equals 2, because these two would cancel. You've got the 1 plus I square root of 2 divided by 1 plus I square root of 2. That just leaves a 2. So working with negative radicals allows us to find complex solutions to quadratic equations. Find all the solutions of the quadratic equation. So for equations like this, this is a quadratic equation. You can use the quadratic formula to find the complex zeros, but you don't have to. There's a quicker way to do it. So you've just got, since you have it all set equal to 0 here, you can just subtract 49 from both sides, which gives you x squared equals -49. And then you've got, anytime it's x squared plus something without an x term, you can do this. As long as it's a square, you can basically just figure out what the complex roots are going to be. So if you've got the square root of -49, if we take x squared and we take the square root, and we got -49, take the square root, that gives us plus or minus the square root of -49. And then we pop out that I from the negative symbol, we pop it outside of the radical. So we've got plus or minus I square root of 49. And we know that the square root of 49 is 7, so we can pop that outside of the radical, and that just gives us plus or minus 7i. And the same thing happens if you were to take a equals 1, b equals 0, and c equals 49, and you plugged it into the quadratic formula, you would still get 0 plus 7i. So you can either do the quadratic formula, or if you're able to recognize when you have just a short quadratic equation like this, try messing around with it to see if you can just find it quickly by popping out I outside of the radical there. So we've got 2x squared minus 2x plus 1. So we've got a equals 2, b equals -2, c equals 1. So we plug it all into the quadratic formula. And then we've got 2 plus the square root of -4 after we subtracted everything over 4. So then we take that I and we pop it outside of the radical. So we've got 2 plus I square root of 4 over 4. And that gives us, the 2 comes outside of the radical and is multiplied into the 2i. So we've got 2 plus 2i over 4. And dividing 2 by 4, we get 1/2. Dividing 2i by 4, we get 1/2 I, plus or minus 1/2 I. Complex zeros in the fundamental theorem of algebra. So let's see, we've got every polynomial with complex coefficients has at least one complex zero. Because any real number is also a complex number, the theorem applies to polynomials with real coefficients as well. If p of x is a polynomial of degree n is greater than 1, there exist complex numbers such that, okay, basically all of this is saying is that polynomials can be factored completely by writing complex zeros in the form x minus c. That's all it's saying. A polynomial p is given. Find all zeros of p, real and complex, and factor p completely. So we've got x to the 4th minus 16. So we know that this is a difference of squares. So we've got x squared plus 4 times x squared minus 4. The zeros of these two quadratic can be found without using the quadratic formula. You just set the equations equal to 0. So this is what we were talking about before. So we can find both of these zeros without using the quadratic formula for either one of these equations. So we've got x squared plus 4 equals 0. So we've got x squared equals -4. X equals plus or minus the square root of -4. Pop the I outside of the radical. So you've got x equals plus or minus I squared of 4. X equals plus or minus 2i. So then over here, this one's pretty easy. You got x squared minus 4. You add 4 to both sides. You got x squared equals 4. So x equals plus or minus 2. So now you know your zeros are -2, 2, -2i, and 2i. So then you plug the zeros into x minus c to factor it completely. So you just take everything and do it as x minus c. So we're going to take our -2 and plug it into x minus c. We're going to take our 2 and plug it into x minus c. Take our -2i and plug it into x minus c, and take our 2i and plug it into x minus c. So that gives us x plus 2, because x minus a -2 is x plus 2. That's why we write it this way. That's why this 0 is -2, is because it's technically in the form x minus c. So then we've got x minus 2, and then we've got x plus 2i, because x minus a -2i is x plus 2i, and then x minus 2i right there. So that's how we factor it completely. All right, we've got x squared plus 2x plus 2. A equals 1, b equals 2, and c equals 2. So we plug it all into the quadratic formula, and then that gives us -1 plus i, because we've got, let's see, after subtracting and doing all our multiplication under the radical here, we get -2 plus or minus square root of -4. Pop out that I outside of the radical to give us I square root of 4. So then that gives us square root of 4 is 2. That gives us -2 plus or minus 2i. Divide everything by 2. That gives us -1 plus or minus i. So now we know our zeros are -1 plus i and -1 minus i. So you plug the zeros into x minus c to factor it completely. So you just set it up with x minus blank and x minus blank, and then you can plug in your zeros. So we've got -1 plus i and -1 minus i. So x minus a -1 is x plus 1. X minus a positive I is x minus i. So then we got x minus a -1 is x plus 1, and x minus a -i is x plus i. So that's how you factor it completely. All right, the zeros theorem. Every n greater than or equal to 1 has exactly n zeros, provided that the zero of multiplicity k is counted k times. So basically that's saying whatever the degree of your polynomial is, that's how many zeros you're going to have. So this is going to be a degree 10 polynomial, because we have 3 plus 5 plus 2. So that's 8 plus 2. So we've got 1 is a 0, and it's of multiplicity 3, because it occurs 3 times, x minus 1 times x minus 1 times x minus 1. And then we've got 2, -2 is a multiplicity 2, and we've got -3 is a multiplicity 5. So we know that it's going to have the same numbers of zeros as its degree. Finding polynomials with specified zeros. So find a polynomial with integer coefficients that satisfies the given conditions. R has a degree 4, and zeros 1 minus 2i and 1, with 1 a 0 of multiplicity 2. So we know that there needs to be 4 zeros total, and you know that 1 will be a 0 twice. And we also know that since 1 minus 2i is a 0, then 1 plus 2i is also a 0, because the complex conjugate also has to be a 0 if there's a complex 0. So we write them all in the form of x minus c. So we've got x minus 1 times x minus 1 times x minus 1 minus 2i times x minus 1 plus 2i. So then that gives us x minus 1 times x minus 1, because 1 occurs twice. And then we've got x minus 1 plus 2i and x minus 1 minus 2i. So then these equations get kind of long. To find out what the polynomial is, you have to multiply all of them together to get the 4th degree polynomial. So work in sections if you need to. So we've got x squared minus 2x plus 1. That's the same thing as x minus 1 times x minus 1. And then we're going to multiply these two together, the x minus 1 plus 2i times x minus 1 plus 2i. So we've got x squared minus x minus 2ix. And then we've got taking -1 times x, we've got minus x again. We've got -1 times -1, which is +1. We've got -1 times -2i, which gives us +2i. And then we're taking this 2i and multiplying it to the x. So we've got plus 2ix. And then we've got plus 2i times negative 1, which gives us negative 2i. And then we've got 2i times the negative 2i, which gives us negative 4i squared. So all these terms highlighted will cancel out. So then we can simplify it. We've got x squared minus 2x plus 1 minus 4i squared. Remember that I squared equals negative 1. So then we can just change this to negative 1, which gives us a negative 4 right here. So it's still x squared minus 2x plus 1 minus negative 4. So that gives us a plus 5. So then we're going to multiply these two together, and we've got x to the fourth minus 2x to the third plus 5x squared minus 2x to the third plus 4x squared minus 10x plus x squared minus 2x plus 5. All right, and then simplifying that, we've got x to the fourth minus 4x to the third plus 10x squared minus 12x minus 5. Just make sure you're distributing properly here every time. Just distributing each term to every other term, and you'll be fine. All right, find all zeros of the polynomial. So anytime we're given that p of x is 2x to the third plus 7x squared plus 12x plus 9. So we'll start with synthetic division and finding possible zeros. So we're going to take the factors of 9 over the factors of 2, and that gives us all these possible candidates for possible zeros. So just saving some time, we find out that by trial and error that negative 3 over 2 is a 0. So we're going to factor it like this: x plus 3 over 2 times 2x squared plus 4x plus 6. So then we're going to use the quadratic formula, and plugging this in for a equals 2, b equals 4, and c equals 6, then we get here to negative 4 plus or minus the square root of negative 32. So we can pop out I outside of that radical right here. So we've got negative 4 plus or minus I square root of 32. And 32 is the same thing as 16 times 2. So then we can take 4 and pop it outside of the radical because the square root of 16 is 4. So we've got negative 4 plus or minus 4i square root of 2 over 4. Divide everything by 4. We get negative 1 plus or minus I square root of 2. So your zeros are negative 3 over 2, negative 1 plus I square root of 2, and negative 1 minus I square root of 2. So same thing that we went over, the conjugate zeros theorem. If a complex number is a 0, then the complex conjugate is also a 0. All right, linear and quadratic factors theorem. So a quadratic polynomial is irreducible if it has no real zeros. It can still be factored with complex zeros. So a polynomial p is given. Factor p into linear and irreducible quadratic factors with real coefficients. Factor p completely into linear factors with complex coefficients. So sometimes you'll be asked to factor it until you can't anymore without going into complex zeros. So if you're doing it without complex zeros, then this quadratic is said to be irreducible over their real numbers. That's what they're asking for when they're asking for something that's irreducible. So we'll start with the factors of negative 9 over the factors of 1. That gives us plus or minus 1, plus or minus 3, and plus or minus 9. So we find out that 1 is a 0 with synthetic division. So then going further, we find out that negative 1 is a 0 with synthetic division. So then we've got x squared plus 9. And we know that x squared plus 9 can't be reduced any further without using complex zeros. So this is the irreducible and the linear terms that they asked for first. So then it says to factor p completely into linear factors with complex coefficients. So to factor it completely, we've got to get this x squared plus 9 into complex zeros. So we take x squared plus 9 equals 0, x squared equals negative 9, x squared equals plus or minus the square root of negative 9, popping I outside of the radical for that negative sign. We've got x equals plus or minus I square root of 9, and square root of 9 is 3, so we've got x equals plus or minus 3i. So the complete factorization, x minus 1 times x plus 1 times x minus 3i times x plus 3i. All right, rational functions. Rational function is of the form r of x equals p of x over d of x. So this is just showing some table values for the function f of x equals 1 over x. It's going to be helpful to remember what the graph of f of x equals 1 over x looks like, because we're going to do transformations to that graph. So this is just saying, this is how we write x approaches 0 from the left. So if we have a little negative superscript right here, x approaches 0 from the left. So you can see that as x is getting, as x is getting smaller, x approaches 0 from the left, then y is approaching negative infinity. So we'll go into that right here. So this is the graph of f of x equals 1 over x. So we can see that f of x approaches 0 as x approaches infinity, and we can see that f of x approaches infinity as x approaches 0 from the right. X is approaching 0 from the right, and f of x is approaching infinity. So then we can see as x approaches 0 from the left, f of x approaches negative infinity. X equals 0 is the vertical asymptote, and y equals 0 is the horizontal asymptote. Definition of vertical and horizontal asymptotes. So it's basically restrictions where your graph is going to exist and not exist. So these are vertical asymptotes. As it approaches a, y approaches infinity. As it approaches a, it's like just a restriction. So let's see, we've got a rational function of this form can be graphed by shifting, stretching, and or reflecting the graph of, okay, when you have r of x equals a of x plus b over c of x plus d, a rational function of this form can be graphed by shifting, stretching, and or reflecting the graph of f of x equals 1 over x. So I'll show you what we mean by that. Use transformations of the graph of f of x equals 1 over x to graph the rational function and state the domain and range. So we've got r of x equals 1 over x plus 1. So since f of x equals 1 over x, we're asked to use transformations to the graph of 1 over x. So if f of x equals 1 over x, then f of x minus 1, if we replace x with x minus 1 everywhere we see an x, then f of x minus 1 equals 1 over x minus 1. So we can obtain the graph for r of x equals 1 over x minus 1 by shifting 1 unit to the right here. This f of x, let me highlight it. This f of x minus 1, that's the same thing as shifting it to the right. So you're just shifting the whole graph. We have this f of x equals 1 over x, and the horizontal asymptote was 0, and the vertical asymptote was 0. So if we're shifting it 1 over to the right, then this vertical asymptote is now going to be x equals 1. So we'll show it down here. So now we've just shifted everything over 1. So now the vertical asymptote, it's still the same thing, but we've shifted it over 1. Here's the domain and range. Now the horizontal asymptote is still y equals 0, and the vertical asymptote is x equals 1. So now we've got s of x equals 3 over x plus 1. So the first thing we're going to do is we're going to factor out a 3 so that we can get 1 over x plus 1. And since f of x equals 1 over x, then f of x plus 1 equals 1 over x plus 1. So basically, it's just like what we were talking about in the beginning with the transformations of graphs. You're trying to get it into this form right here so you know how the graph is going to be shifted, reflected, everything like that. So you've got 3 times f of x plus 1, because since f of x is 1 over x, then f of x plus 1 is 1 over x plus 1. And then remember, we factored out a 3, so 3 times all of that. So we know it's going to be stretched vertically by a factor of 3 and shifted to the left 1 unit. So now our vertical asymptote is x equals negative 1 because it was shifted right here. We're just shifting it over, and then we're stretching it vertically by a factor of 3. Okay, t of x equals 2x minus 3 over x minus 2. For these ones, you can use long division to figure out the transformation to f of x. And so we're just going to go ahead and divide 2x minus 3 over x minus 2. So we've got x goes into 2x 2 times. And so 2 times x minus 2 is 2x minus 4. Subtracting these, we get 1. So t of x equals 2 plus, this is just like the p of x over d of x that we were talking about. P of x over d of x equals the quotient plus the remainder over the divisor. So that's the same thing that we were talking about before. So then we can rearrange these terms and say that it's 1 over x minus 2 plus 2. Since f of x equals 1 over x, then f of x minus 2 equals 1 over x minus 2. So then it would be f of x minus 2 plus 2. So that's how our graph is shifted. So we know that it's going to be shifted to the right 2 units. So we know that our our vertical asymptote is going to be x equals 2. and it's also shifted up 2 units. So we know that our horizontal asymptote was y equals 0, but now it's going to be y equals 2 because we shifted up. So it's still the same graph behavior as 1 over x, but we've done some shifting here. All right, intercepts of rational functions. X-intercepts can be found by setting y equal to 0, and y-intercepts can be found by setting x equal to 0. Find the x and y-intercepts of the rational function. T of x equals x squared minus x minus 2 over x minus 6. So to find the x-intercepts, we're going to set the whole equation equal to 0. T of x or f of the same thing as y. So we're going to set everything equal to 0. So we've got 0 equals x squared minus x minus 2. So we're multiplying both sides by x minus 6. And 0 times x minus 6 is still 0. So we've got 0 equals x squared minus x minus 2. And that can be factored. So we've got x minus 2 times x minus 1. So then we know that our x-intercepts are going to be 2 and negative 1. So y-intercepts, we're going to set x equal to 0. So we're going to do t of 0. So we're just going to plug in everywhere we see an x, we're going to put a 0 in there. So then we've got 0 squared minus 0 minus 2 over 0 minus 6. That's going to give us a negative 2 over negative 6, which is positive 1/3. So we've got x-intercepts 2 comma 0 and negative 1 comma 0. And then our y-intercept is 0 comma 1/3. Same thing here. We've got x-intercepts. We're setting y equal to 0. We've got x squared minus 9 over x squared. So we're set the whole thing equal to 0. Multiply both sides by x squared. That gives us 0 equals x squared minus 9. Adding 9 to both sides. So then we get, taking the square root, we've got x equals plus or minus 3. The y-intercept is x equal, we're going to set x equal to 0. So we take r of 0. We're just going to plug in 0 everywhere we see an x. So then we've got, it's undefined, because we can't divide by 0. So there is no y-intercept. Sometimes you'll get that. If anytime there's something undefined, like x-intercepts, if you have negative under the radical, or y-intercepts, if you have 0 in the denominator, then there's not going to be a y-intercept or an x-intercept if it's undefined. So we've got x-intercepts 3 comma 0 and negative 3 comma 0, and there's no y-intercept. Vertical asymptotes are found by factoring the denominator and finding the zeros. And horizontal asymptotes depend on the degree of the numerator and the denominator. So just remember, with vertical asymptotes, you're always going to be looking at the zeros for the denominator. And then horizontal asymptotes, you're going to be comparing the degree of the numerator and the denominator to know what you're going to do. So again, right here, finding asymptotes of rational functions. So if the numerator degree is less than the degree of the denominator, then it's going to be y equals 0. If the numerator degree equals the denominator degree, it's going to be a ratio of the leading coefficients. And if the numerator degree is greater than the denominator degree, then there's going to be no horizontal asymptote. So remember, less, if numerator is less, y equals 0. If they're equal to each other, it's going to be a ratio of the coefficients. If the numerator is greater than the denominator, there's no horizontal asymptote. Finding all horizontal and vertical asymptotes, if any. So we've got s of x equals 6x squared plus 1 over 2x squared plus x minus 1. So factor the denominator for vertical asymptotes. So we're going to factor this 2x squared plus x minus 1. So that gives us 2x minus 1 times x plus 1. And so that tells us that the zeros right here, we're going to have 1/2 because 2x minus 1. And then we're going to have negative 1. So those are going to be your vertical asymptotes, just the zeros of the denominator. So both the numerator and the denominator degree are 2 because we've got 6x squared and we've got 2x squared. So since they're equal, we're going to take a ratio of those leading coefficients. So it's going to be 6 over 2. Ratio of the leading coefficients, that's going to be 3. So y equals 3 is a horizontal asymptote. Okay, trying another one. 6x to the third minus 2 over 2x to the third plus 5x squared plus 6x. We're going to factor the denominator. We can factor out an x. And then there's no other real roots because 2x squared plus 5x plus 6 can't be factored further over the real numbers. So the only vertical asymptote is going to be x equals 0. So both the numerator and the denominator are degree 3. So since they're equal, we're going to take a ratio of the leading coefficients. So it's going to be 6 over 2, which is 3. So y equals 3 is a horizontal asymptote. So then we got one more. T of x equals x squared plus 2 over x minus 1. So we already know that x equals 1 is a vertical asymptote looking at the denominator. And since the numerator degree is greater than the denominator, we got x squared compared to x, then there's no horizontal asymptote. All right, sketching graphs of rational functions. The first thing you want to do is factor the numerator and the denominator. You want to find the x-intercepts by determining the zeros of the numerator and the y-intercepts from the value of the function. Just like we talked about, for y-intercepts, you're going to set x equal to 0, and for x-intercepts, you're going to set y equal to 0. So finding the intercepts, you're going to find the vertical and horizontal asymptotes, and then sketch the graph. So common factors in the numerator and denominator. This is when holes occur in the graph. So common factors can be factored out to simplify the function, but this leaves a hole in the graph for that x value. So if we have s of x equals x minus 3 over x squared minus 3x, and we factor these, we're going to factor both the numerator and the denominator. This one can't be factored, but the bottom one can. We can factor out an x. So then we've got x times x minus 3, and then we cancel out x minus 3 in the numerator and the denominator. So then we're left with 1 over x, but x cannot equal 3 now because that's a 0 of whatever we canceled out. So if you're canceling out common factors in the numerator and the denominator, your graph is going to have a hole at whatever 0 that you canceled out. So same thing here. If we were to factor this top one here, the x minus 2 cancels and the x minus 2 cancels. So then we're left with x squared, and x cannot equal 2. So we'll go over graphs with holes. Here's those two that we just talked about. X is not defined. There's a hole right here for x equals 3. So anytime x equals 3, that's not defined. Same thing here for x equals 2. X is not defined. There's going to be a hole right there in the graph. So find factors that are common in the numerator and denominator, then find the intercepts and asymptotes and sketch a graph of the rational function. State the domain and range of the function. So we're given r of x equals x squared plus 4x minus 5 over x squared plus x minus 2. So we're going to factor the numerator and the denominator. So after we factor, we find x plus 5 times x plus 1, x minus 1 over x plus 2 times x minus 1. So the x minus 1s are going to cancel out, but that's going to leave a hole at x equals 1. Whatever that 0 is, it's going to leave a hole at x equals 1. So to find out where exactly the hole occurs, you're going to plug x equals 1 into the function. So your function now is, since we canceled out those common factors, your function has changed. So your function is now just x plus 5 over x plus 2. And with x cannot equal 1. So now we're going to plug in x equals 1 to find out exactly where on the graph that hole occurs. So we need to find out what the y value is to find out the point. So we're going to plug in x equals 1. So we're going to do 1 plus 5 over 1 plus 2, which equals 6 over 3, which equals 2. So now we know that that's our y value for this x value, and that's exactly where the hole occurs. So the hole occurs at 1, 2 on the graph, and the vertical asymptote is x equals -2, because we've got this in the denominator. So remember, denominator is the zeros of the denominator or the vertical asymptotes. So vertical asymptote is going to be x equals -2. So the horizontal asymptote, since we've got x squared over x squared and both of the leading coefficients are 1, it's going to be a ratio of the coefficients. So we've got 1 over 1 equals 1 and y equals 1. So for the y-intercept, we're going to set x equal to 0. Remember, your function has changed. You don't have to use this original one anymore. When you're canceling out common factors, you're going to stick with whatever you canceled out and just remember that it can't equal this wherever the hole is at. So now we're going to do our x-intercepts for y equals 0. So we're going to set the whole thing equal to 0. 0 equals x plus 5 over x plus 2. So we've got multiplying both sides by x plus 2. We've got 0 equals x plus 5. And we've got x equals -5 if we subtract -5 from both, or subtract 5 from both sides. So notice that this is a transformation to the graph of f of x equals 1 over x. So we can do this by long division again. So x plus 5 divided by x plus 2. So we've got x goes into x one time. 1 times x plus 2 is x plus 2. X plus 5 minus x plus 2 is 3. So then we know that this r of x that we have, x plus 5 over x plus 2, is going to be 1, which is the quotient, plus 3, which is the remainder, over the divisor. So then we can rearrange it to do 3 over x plus 2, just like we were when we were transforming the 1 over x before, the graph of 1 over x. So then we can factor out a 3. So we've got 3 times 1 over x plus 2 plus 1. And since f of x equals 1 over x, then f of x plus 2 equals 1 over x plus 2. So the transformation to the graph of f of x equals 1 over x is 3 times f of x plus 2 plus 1. It's shifted to the left 2 units, it's shifted up 1 unit, and it's stretched vertically by a factor of 3. So doing this gives you the shape of the graph. So that really gives you all the information you need to graph a function. Like as long as you mark your x-intercepts, you mark your asymptotes, and you know the behavior of the function, since you know what the graph is going to look like because you know it's a transformation to 1 over x. So it's going to look just like 1 over x. And if you've got your y-intercept, you've got your hole right here at, what was it? Where did we say the hole was at? Hole occurs at 1, 2 on the graph. 1, 2. So there's going to be a hole right there on the graph. All right, and then slant asymptotes. If r of x equals p of x over q of x is a rational function with the degree of the denominator is more than, let's see. All right, so let's go ahead and talk slant asymptotes. If the numerator is greater than the denominator by exactly 1 degree, then there is a slant asymptote. So let's say that, I don't know if I have an example of one or not. Find the slant asymptote by using long division. Quotient is a slant asymptote line. So this is just like p of x over d of x equals q of x plus r of x over d of x. So if we're given r of x equals x squared minus 4x minus 5 over x minus 3. So we're just going to do this long division style. We're just going to divide this by x minus 3. So doing the long division, we get the quotient x plus x minus 1, and we get a remainder of negative 8. So then we can rewrite this just like we did the quotient plus the remainder over the divisor. So we've got, here's the quotient, x minus 1 minus the remainder over the divisor. So then we know that this right here, this x minus 1, that's going to be your slant asymptote. Don't worry about the remainder. You're just trying to find out what this ax plus b is right here. So that's going to be your slant asymptote, the ax plus b. And then you just want to make sure that you write it in that form with your quotient. It's really whatever your quotient is going to be the slant asymptote. So let's see, factor, this is just the steps on how to find, on how to get everything that you need to graph it and find the slant asymptote. So this is the x-intercepts, the y-intercept, vertical asymptote, the behavior, the horizontal asymptote, and the slant asymptote. So then you can see, graphing all this, this is the line x minus 1. There's a slant asymptote that exists right there. And that's because the degree is 1 less, if the degree in the denominator is 1 less than the degree in the numerator. So that's the slant asymptote. So the last thing that we're going to go over is determining the domain and range from a graph. I know that this was a little bit difficult on some of the WebAssign homeworks. So the domain is wherever the x values exist. So here you can look at it, and it's pretty much stretching from negative infinity all the way to positive infinity. But we have some restrictions here. It looks like x can equal -1 and x can equal 7. So our domain is going to be negative infinity, comma -1, union -1, comma 7. Union 7, comma infinity. So that's our domain. So for the range is wherever the y values exist. So y cannot equal 0. That's our horizontal asymptote. And y does not exist between -1/2 and 0. So we've got about -1/2 right here and 0. There's nowhere, the graph does not exist here because there's no y values that exist for any of these y values right here. There's just the graph doesn't exist there. So -1/2 is included on the graph because the graph exists there. See, that's where the vertex is at -1/2. So the range is going to be negative infinity because we're starting all the way down here, negative infinity, all the way up to -1/2, and it's included. So we use a bracket, and then we've got 0 to infinity because we're starting right here again at 0 all the way to infinity is where the graph exists. And then this one, sometimes this was something interesting that I found. A common mistake that students make is to think that the graph cannot cross a slant or horizontal asymptote. This is not the case. A graph can cross a slant and horizontal asymptotes, sometimes more than once, but it can't cross a vertical asymptote. So just if you ever see a graph like this and you're wondering why it's crossing an asymptote, graphs can cross horizontal and slant asymptotes, but they cannot cross vertical asymptotes. So just something to remember. So it's a little bit more difficult trying to figure out the range on this one because it's the horizontal asymptote might kind of throw you off. But so the domain is pretty easy because you can see it's got the vertical asymptotes here. So we've got x can equal -1 and x can equal 3. So it's just going to be negative infinity to -1 and union -1 to 3, union 3 to infinity. So for the range, it's going to go negative infinity all the way up to about -1.7. And that's going to be a bracket because it's included there. And then it's going to be union all the way up to 2.3 to infinity. So this is about 2.3. And we've got, it exists at 2.3. So we're going to have a bracket there and it goes all the way up to infinity. So just basically wherever your y values exist, wherever you have a graph exists, that's going to be your range. And wherever the empty spaces are where the graph doesn't exist, that's not going to be included in your range. So that's pretty much all I got for this module. Sorry it took so long to kind of explain everything, but hopefully that was a good review for everybody. Does anybody have any questions on anything that we went over?
So when you're looking at a graph, like on the last page where it has the range and you can't really tell what exactly the values are those just estimated?
Yeah, on WebAssign, it pretty much was like that. Like it was just estimated. That I took it straight from the homework, but I doubt we'll get a question like that on the exam. But yeah, those are just estimated values. You're talking about like this -1.7 and this 2. Yeah, those are just estimated.
Because I had a question on the WebAssign that was asking me that range, and it wasn't, I don't know how to find the range just from like a graph like that, but the value that the answer was looking for was like -16/25, and I had no idea how to find that.
I think on some of those questions on WebAssign too, it said to use a graphing device, which is a graphing calculator to kind of estimate it. And I ended up having to do that to estimate them. Like I ended up having to take, and actually zoom in on it and like use the graphing calculator to just find out kind of where it was and then estimate a decimal. That's pretty much what I did on those.
Okay.
But I doubt it's gonna. I really highly doubt it's gonna be that difficult on a. I doubt we'll even get estimated values, and if they are, they're not gonna be given to us, on multiple choice. So.
Right. Okay.
Does anybody have any other questions? All right. Well, thank you guys so much for coming to the study session. If there's no other questions or anything that anybody else wants to go over, then that's all I got.
I know that was so much.
Yeah, I was gonna say I'm gonna have to go through it again. It was a lot.
Thank you, Becca.
Yeah, no problem, y'all. And I posted the whole study plan in the group chat. Just make sure you download it so you can see all the equations, and then I'd be down for that.
Yeah, that's cool.
Yeah.
Yeah, let's do it.
That.
Sounds good to me. And if you guys have any questions too, feel free to message me directly and group me, and I can help however I can.
Sweet.
Yes. Well, good luck.
All right, y'all. It's been real.
Yeah.
Have through Monday to take the test.
What's that?
We have through Monday to take it.
Yeah.